first colloquium of this academic year. Today's event is devoted to, as you will see, two aspects of quantum gravity. I will give you some details about the speaker shortly. I just want to anticipate that the next two events will take place in November, actually November 15. The next one will be devoted to chemistry, and then there will be another event devoted to computer science, we can say, in December. I think it's December 17, if I'm correct. So very briefly, I would like to introduce today's speaker. Professor Nicolai was a student of Julius Wess, who was one of the inventors of supersymmetry. And then he worked for some years at CERN, and before becoming a professor at the Second Institute for Theoretical Physics in Hamburg, but when Germany was unified, was one of the first eminent people to move eastward, and he became one of the directors of the Max Planck Institute in Golm, also called the Albert Einstein Institute. Professor Nicolai is stands out, I would say, in the community of people that have devoted their efforts to supersymmetry and supergravity for two reasons. He has a wider perspective than many of the other people, because for one matter, he anticipated very important work on membranes when people were not taking this system seriously, and also he looked beyond the corners of this approach, and he's one of the people that really are familiar with other aspects like attempts to canonically quantize gravity, what people call loop quantum gravity loosely, and he has given a number of contributions to these fields, starting from the famous original gauging of n=8 supergravity to the study of its compactifications, to the first properties of these membrane systems, to various studies of consistent extensions to beyond 4 dimensions, and to the study of infinite dimensional Lie algebras that occur in this context, a very complicated subject that is still at its beginnings and has to do with some duality properties of these systems. For his contributions, he received a number of awards, which include the Einstein Medal, and recently he's directing some effort in these fields with an ERC grant that was awarded to him, I think, a year ago or so. Thank you, Hermann. I'll go there and I will.
Okay, can you hear me? Well, thank you very much for this introduction, for the kind invitation to give this colloquium. And this is probably one of the most splendid lecture halls I've ever given a lecture in, a colloquium in. My subject today is the question of whether we can unify physics. Of course, this could mean a number of things, but to put it in very simple terms, the question is, can we really reduce
Alternatively, do it with this.
Yes, no, better? Is this better? So you can hear me. Okay, very good. So the subject today is symmetry and unification. Now we also have to make sure that this works. Doesn't seem to be. Okay. No. Yeah, my subject today is symmetry and unification, the question whether physics can be unified. And there's also a question what you mean by unifying the physical laws into a single law. Now, attempts to understand physics or natural laws really in a holistic or unified way have a long history that reaches back to ancient times. You've all heard about the 4 elements of Empedocles, and at the same time there was a similar proposal in China. It's referred to as Taoism, and they use 5 elements. 4 of the 5 elements are the same as in Empedocles' scheme, and interestingly the 5th was the vacuum. So this is anticipation of something that was realized only fully realized only 2,000 years later. But the real attempts, or more recent attempts, to unify natural laws start with the beginning of modern physics. There is Galileo and Newton, and the first, in some sense, the first attempt in this framework was Laplace, who, knowing the laws of mechanics of Newton and Galilei, made the hypothesis or postulated that the world should be understood as in the same way as a mechanical clock, which simply follows the laws of Newtonian physics. So it was set up by some creator and then set in motion, and from that point onwards it just moves forward following the laws of classical physics. Now, of course, it was soon realized that there was more in the world than just Newtonian mechanics. The beginnings of the 19th century, it was electromagnetism, and electromagnetism was unified into the so-called Maxwell Laws in around 1860. And that again led to the view towards the end of the 19th century that one had more or less understood everything. There's a famous story about Max Planck, because when Max Planck was a student, he wanted to take up studies of physics. He went to a professor in Munich and asked, his name was Joly, and he asked him, what are the prospects in this field? Does it make sense to start studying physics? And then he was told, no, actually not, because with Newtonian mechanics and Maxwell's equations, more or less everything was understood. But as you know, this turned out to be completely wrong. And
don't name the name of the professor.
Pardon?
You don't name the professor.
I did.
You did?
Yes, Joly. He's completely unknown. This is the main thing he's known for. It's a wrong prediction, actually. Anyways, so Planck didn't, he wasn't discouraged, and as you know, he discovered quantum mechanics. And this was precisely in 1900. And then came, of course, the revolution of quantum mechanics. There came the revolution of special relativity and general relativity. And already in 1918, Hermann Weil wrote a book with the title Space-Time Matter, with the idea that not only space and time should somehow, the laws that Einstein had discovered should not only apply to space and time, but should also in some sense encompass the description of matter. And then Einstein himself spent the last 26 years of his life searching in vain for a unified theory. Well, it didn't stop there. There was a famous attempt by Heisenberg in 1958. This was termed Weltformel. This is the German term for what's now called theory of everything. And that was also a failure. At the same time, around the same time, people for the first time tried to apply quantum mechanics to general relativity. This was work of Dirac originally, but then in particular Wheeler and DeWitt, who came up with the kind of Schrödinger equation for, proposed Schrödinger kind of equation for quantum gravity. And since the 1960s, late 1960s, we've had string theory. This is an ongoing effort. This effort has now been going on for 50 years. Now, I'm just showing you this. This is a photograph of Einstein's presentation of his proposal in 1958. And I'm showing you this, first of all, pardon? This is Heisenberg, sorry, Heisenberg. I'm showing this because when I say, unified single formula, you might just ask what would it look like? And here you have a concrete example what it would look like. This is the, well, of course, you talking with the hindsight of, looking back. Anyway, this is something called nonlinear spinor equation, and this is something Heisenberg came up with and proposed actually as a theory of everything, actually leaving out gravity, but he was mainly concerned with the nuclear forces. The second reason I'm showing this is that by now we're getting much better with PR, especially our colleagues from the US. But I think this was the only time that a theory of everything so far has been announced with the support of a symphony orchestra, because this is hard to recognize, but here you see the contrabass, and here's the orchestra, and Heisenberg is sitting right here. So there's still good ideas as far as PR is concerned.
Where was that?
This was in 1958, a good question. I think it was a meeting of the German Physical Society, but at the same time there was this, I don't know how this symphony orchestra got there, but they somehow, it was put together in somewhat hastily. Anyway, we now know that attempt also failed because very soon objections were raised against this proposal. Well, central notion of my colloquium is that of symmetry, and here I've simply taken a definition from what you find in Wikipedia. When you talk, what do we mean by symmetry? It comes from the Greek. By this we mean, in everyday language at least, it refers to a sense of harmonious and beautiful proportion and balance, like what you see in this lecture hall. And in mathematics, symmetry has a more precise definition that an object is invariant to any of various transformations, including reflection, rotation, or scaling. And for the mathematical formulation of symmetry, the essential notion is that of a group. And this means that this is a consequence of the fact that symmetry operations can be composed, so they can you can compose two symmetry operations to generate a third one. So this is the product. A and B are combined into the product. And you can also invert a symmetry transformation, sort of undo it, going backwards. And furthermore, and this is a mathematical hypothesis, these operations are supposed to obey the laws of associativity, which is written here, but not necessarily the law of commutativity, which is here. This is already obvious when you think about rotations in space, and you think about rotations about two orthogonal axes, and you do them in different orders, then the result will be different. So it means already the rotation group in three-dimensional space would not obey this, or does not obey this property. Well, symmetry is also something that we associate with beauty. So here I show you one particular example. This is a beautiful diagram. It is it's derived from Lie algebra, and the maximal exceptional Lie algebra that occurs in the classification of symmetry groups and symmetry Lie algebra, and it's a projection of the root system of this algebra. This is the root system lives in an 8-dimensional space. You can think of it as an 8-dimensional diamond with 240 corners, and then you project this onto a 2-dimensional surface in this 8-dimensional space, and this is what you get. Now, physicists distinguish between two different kinds of symmetries. We've been talking about operations, symmetry operations that preserve structures. And so the first examples of symmetries arose in realizing these operations in physical space and time. That's why they're called space-time symmetries. And in particular, this applies to rotations in space and translations in space and time. And this is a symmetry that underlies Galilean and Newtonian mechanics. And every physicist, every physics student knows that symmetries are associated with conservation laws. This is called Neuters Theorem. And this is actually what enables us to solve the two-body problem of Newtonian mechanics. Newton was able to derive from his law of gravity, the gravitational force, goes like 1 over r squared. He was able to derive that planets move on elliptical orbits or parabolic, or if they're comets, they could move on hyperbolic orbits. In any case, so this allows a complete solution of what's called the two-body problem in classical mechanics. In terms of space-time symmetries, a great revolution occurred in around 1905, when Einstein modified this mechanics to formulate special relativity. And special relativity unifies space and time into space-time. This was considered separate in Galilean and Newtonian mechanics. And he started with the postulate that the speed of light is constant in any system of reference. Thereby, with a speed, you have a unit that allows you to convert units of length into units of time, so time and space are really the same. So this was an important insight into the kinematics of space and time that, interestingly, philosophers who had worried about this for 2,000 years had not realized. And 10 years later, he took an even more radical step by replacing what's called flat space-time by curved space-time, and postulated that space-time is no longer just the arena in which things happen or occur, but that space-time itself becomes part of the dynamics in the sense that that space-time, the geometry of space-time, gets deformed by the matter that is inside space and time. This has led to the famous Einstein equations governing the gravitational field. Now, so you see here took a step from kinematics to dynamics, because here still in special relativity, space-time is just an arena where things happen. So that's space-time symmetries, but then physicists also somewhat later discovered that there are other kinds of symmetries, and they're referred to as internal symmetries. And this is something that goes back to Heisenberg in the early 1930s, because in those at that time the neutron was discovered, and the neutron was also measured. The mass of the neutron was measured, and it turned out that the neutron mass differs only by 1 per mil from the proton mass, so it's almost the same. And then Heisenberg said the only difference between the neutron and proton is the electrical charge of the proton. The neutron is neutral. And therefore, let me hypothesize, if I could switch off the charge of the proton, then the proton would become indistinguishable from the neutron. And therefore, there should be a symmetry that he referred to, originally called isotopic spin, has been abbreviated to isospin symmetry, relating protons to neutrons and their rotations in this abstract space that rotate protons into neutrons. And from then, of course, he immediately had the idea that the theory of strong forces, which didn't exist at that time, should allow or admit this kind of invariance. And some 20 years later or so, it turned out this was extremely fruitful a concept, because it was picked up in particular by Gell-Mann when he studied the strong interactions and introduced new quantum numbers and enlarged this SU2 to SU3. And then you can come up with such diagrams. They're really, in mathematical language, they're just the root diagrams of this group, or also weight diagrams if you look at other kinds of excitations. And this route has proven to be extremely fruitful, because it has led to the standard model, where these group structures have been generalized to what's now considered to be the symmetry of a theory of particle physics, which is the so-called standard model. So this describes what we know, what we see at the moment. And it was also turned out that there's a threefold reduplication of the fermion multiplets. And we're still debating whether there's also symmetry relating these generations. So this is where we are now with our understanding of nature. These are the fundamental particles, or at least considered to be fundamental right now, the matter particles, and in the red column you see the gauge vector bosons that mediate the forces, and then here's the Higgs boson. And the question is, of course, or will there ever be a symmetry that can explain this as we find it? So this is where we stand at the moment with our understanding of natural laws. The known laws of physics describe observations over a huge range of distances from fractions of a proton diameter to the visible horizon of our universe, a huge factor, and they do so in a quantitatively correct manner. It's not just that we understand qualitatively what's there, we're actually able to calculate, to predict things. General relativity explains the world, the macrocosm, via the curvature of space and time. It's considered to be the most beautiful of all existing physical theories. It's very complicated, the mathematics, but it's based on two extremely simple principles, namely general covariance and the equivalence principle, according to which all bodies fall at the same speed. Actually, Galileo's discovery. And for the very small, it's quantum mechanics and the standard model of particle physics, which unifies quantum mechanics and special relativity to describe matter, quarks and leptons, fermions, and forces, electromagnetic, weak and strong, in terms of a gauge theory based on this group. However, so this is a great success, and it's getting greater every moment that LHC does not discover new things. But we know that this picture has to be incomplete. For one reason, in general relativity, space-time singularities, which is what occurs inside a black hole, are unavoidable with generic initial conditions, so gravitational collapse and black holes. And as proven by Hawking, Penrose, and others in the 60s, and this means that the known laws of physics end at the singularity. You fall into the black hole, and after a finite amount of time, proper time, you hit the singularity, and then we have no way to predict what will happen. Same thing on the other side with the standard model of particle physics, which works extremely well. That's been more and more strongly confirmed by LHC experiments. But we believe, or many of us believe, it's not a mathematically well-defined theory beyond perturbation theory. So you might wonder, why is this? Well, I mean, first of all, it's a fact, but certainly there's possible origin of these difficulties, namely the fact that in both general relativity and standard model, we think of the space-time as a continuum, differential manifold, which means you can divide it up into you can go to as small distances as you like. And furthermore, in quantum field theory, elementary particles are really treated as point-like objects, no extension whatsoever. And this is the origin of divergences, infinities that we encounter when we do calculation in the standard model. Now, most physicists believe that something dramatic happens at the Planck scale, which is something if you take the three fundamental constants, Newton constant, speed of light, h bar, and form something of the dimension of a length, then this is what you get. This is what Planck already calculated. And a large majority of theoretical physicists believes that at this scale something dramatic must happen. In particular, it could be that space-time all of a sudden reveals a granular structure and ceases to be a continuum. So that's the question. But in trying to answer the question, we encounter some difficulties. And they're both at the conceptual level as well as at the mathematical level. So maybe the conceptual conflicts are even greater than the mathematical difficulties. We have a conflict between quantum mechanics, which is a probabilistic theory, whereas general relativity is a classically deterministic theory. So how to reconcile these 2 points of view is not so clear. The second point is that if you try to apply quantum mechanics and the probabilistic interpretation of quantum mechanics to the universe as a whole, you also encounter difficulties. If you read Landau-Lifshitz, volume 3, they tell you that it's an essential part of every quantum system that there's an outside observer that you can consider to be described by classical physics. And that person looks at the quantum system, does measurements. This clearly is not true if you think about the universe as a quantum system, as a whole, as a quantum system. And so the question is, what is the meaning of this wave function of the universe if you think that the whole universe is described by a single wave function? And then there's, of course, the question whether the singularities, black hole singularities, and of course also Big Bang singularities, can be possibly resolved by quantum theory. On the mathematical side, there's of course the distinguishing feature of gravity, which sets it apart from the matter interactions. It's the non-renormalizability. And you see here this famous two-loop counterterm from 1983, Gorov-Zaniotti. This means that whatever calculation we want to do in quantized, perturbatively quantized gravity, at each order we have to correct by such a term, and these terms get more and more complicated as you go up in order. So if you want to make a useful prediction for, say, two graviton scattering at two loops, then you will have to take into account this correction. There's also a more canonical approach. I've already mentioned the Wheeler-DeWitt equation, which is a kind of Schrödinger equation for quantum gravity. So you might say, well, that's fine. Now we have something that also describes gravity. The problem with it is that this is ill-defined even by the sloppy standards of physicists. So no one has been able to make sense of this or define it in a mathematically precise way and in a way that is physically sensible. This is also important. So this is where we are, and therefore people have been trying all kinds of things to overcome these difficulties, but the focus is symmetry. The idea being that somehow if we make the laws of nature more and more symmetric, then this might eventually help us to resolve these difficulties. At this point, then in some sense you might claim that symmetry is the most successful principle of all physical theories. Because if you look at the evolution of what we've learned about physical laws, it's also been an enhancement of symmetry. Without notions of symmetry, we would not even be able to formulate Young-Mills theories or the standard model of particle physics. We would not be able to formulate the Einstein field equations. We would not be able to predict, say, for example, how a photon interacts with gravitation. So I think it's a hypothesis at this point, but I think a very plausible hypothesis that one possible way to take is to look for symmetry enhancement as a guiding principle. So this has been tried, and this has been something that's been going on for, well, 40, 50, 60 years. And I give you just some examples, some of the ideas that have been tried or are still around. In some sense, the most direct one, if you just look at particle physics, you see this is the a gauge group of the standard model. It doesn't strike you as particularly distinguished. And therefore, first of all, it's also a factor of 3 groups. So the first thing you might try is to embed this standard model group into a simple group. And this was a proposal that was made in the early 70s. And it was really kind of beautiful idea because it leads to further unification beyond the unification that you see in the standard model, namely unifies quarks and leptons into single multiplets. It also predicts proton decay, and this is a prediction that has not come true. People have been looking for the proton decay for the last 30 years or so, but to this date, the proton simply refuses to decay. So this theory is probably out, but this enlargement is still alive, I think, in some versions. But even SO10, you might say, what's so special about SO10? That's the rotation group in 10 dimensions. So it's an internal space, as I said, not physical space-time. But then you can go even further and then embed it into one of the exceptional groups. This is, this is plausible because if you're looking for groups, I mean, this should not go on forever. So you would like to have some group there that is somehow distinguished, and we have the exceptional Lie groups in physics, so maybe that's the way to go. So that's one idea that has been pursued. The other idea is merging space-time and eternal symmetries. There's supersymmetry, but this will be given a separate slide. But the earliest attempt in this direction goes back to Kaluza and Klein, or rather Oskar Klein, in 1921. He had the idea to take the Einstein equations, but not in four-dimensional space-time, but increase space-time by one dimension. So look at Einstein's equations in five-dimensional space-time, and then analyze it from a four-dimensional point of view. And then it turns out that that theory describes not just four-dimensional gravity, but electromagnetism, Maxwell equations, also with their correct coupling to gravity. And this idea was refined in the 30s it was Kaluza who had this idea in 1921. I said it the wrong way around. Oskar Klein came in the 1930s and extended it to higher dimensional spaces, internal spaces, and also non-abelian groups. And this is an idea that, although we have no evidence so far that this works, it continues to hold fascination, because somehow the idea is that if we can understand the symmetry groups that we see in particle physics in a geometric way as coming from some higher dimensional geometry, that's certainly a fascinating thought. And now here, some says the most important discovery, even though it doesn't look like, or didn't look like it at the time, is the discovery of duality symmetry by Dirac in the 30s. He noticed that in Maxwell equations you have an electric and magnetic field. And he noticed that the equations in empty space allow an extra symmetry whereby you rotate the electric and magnetic fields into one another. This is something, the simplest example of what's now referred to as a duality symmetry. And if you extend it to the charges, it means that you are sort of forced to introduce on top of the electric charges also magnetic charges. And the duality symmetry rotates the electric into the magnetic charges. Now, we haven't seen magnetic charges so far, also another thing that people have been looking for, but it has turned out that in modern superstring, supergravity theories, these symmetries play an extremely important role. And then there's, of course, the theory that, well, maybe you even have to quantize the notion of symmetry. I remember a lecture by Yuri Manin, famous mathematician, in Hamburg, and he started his lecture by saying, we must quantize mathematics. It's like, in physics, we have classical physics, but that's not quite right. We have to quantize it. And maybe you also need to do this with, well, symmetry notions, groups, and also maybe with space-time itself. So that's another a line of research that people have taken. And the question is really, is it possible to determine the right theory, hopefully with a standard model as the answer, purely from symmetry principles alone? And it really amounts to something like the search for exceptionality in physics. So here's a picture, at least this was the way people thought about this unification, certainly in connection with grand unification. And the idea is the following. So here you see the evolution of the universe. So the axis, if you go in the right direction, the axis measures time. If you go in the left direction, the axis goes in the direction of increasing energy. And the idea being that here at the beginning, there's a highly unified theory at the beginning of the universe. And then from that moment on, the universe cools down, symmetries get broken in a cascade-like fashion. And so that first of all, the gravity splits off from the other forces. So here there's a single force, then gravity splits off, then you have the matter forces, and the matter forces then split into strong and electroweak. And finally, electroweak splits into electric and weak force. This picture, experimentally speaking, has only been validated up to this point. So you can view it in both ways. Pardon? This, this is, I took this out of an article I had written in German. So here at this point, the electromagnetic and the weak force split. So this happens around the energy that CERN was able to access some 30 years ago. And now we've been going a little further. The next step would be to unify strong and electroweak. According to the gut paradigm, this should happen at 10 to the 15 GeV. So that's somehow the picture. Maybe the picture is still true, maybe not precisely in this fashion. Maybe there are other forces that we haven't seen yet that could pop up here. So that's an entirely open question. So I said supersymmetry deserves a separate slide because this has been the dominant theme of particle physics for the last 40 or 45 years. It's certainly one of the most important developments in mathematical physics. It has not only contributed to particle physics, but inspired a lot of mathematics. Quite a few of the Fields Medal winners of the past years got at least their inspiration from supersymmetry and superstring theory. It's a further unification because it relates bosons to fermions, at the same time forces to matter. This is something we didn't have before, that we can sort of unify the vector bosons, maybe graviton, by symmetry transformations, relate them to the matter fields, the quarks and leptons. Well, and one advantage is that these theories offer the possibility to overcome some of the mathematical difficulties, like this famous two-loop counterterm, by cancellation of bosonic and fermion contributions to Feynman diagrams. So it's believed to be an essential ingredient in constructing a perturbatively consistent theory of quantum gravity. And of course, discovery of supersymmetric partners would revolutionize physics. So here I have a short one-slide introduction to what supersymmetry is for non-experts. The funny thing about supersymmetry is that you now need to introduce new kind of numbers, namely anti-commuting numbers. Normal numbers commute when you multiply them. 3 times 4 is the same as 4 times 3. But it's not so with these anti-commuting numbers, because every time you commute them, you get a minus sign. And this is the mathematical expression of the Pauli principle, because as you can see, as a consequence, if you square one of these numbers, you get 0. And this is the Pauli principle, because Pauli principle says you can only put one excitation into a given state. Simplest example is supersymmetric quantum mechanics. So what you do, you have a Hamiltonian that describes your system. And in some sense, what you do, you take the square root of this Hamiltonian by introducing 2 fermionic operators, which anti-commute in this way to give you a Hamiltonian. So this is the simplest realization of a supersymmetric system in physics. And just like with every symmetry, it's accompanied by degeneracy in the energy levels. If you take an energy eigenstate and transform it with one of these operators. You will transform a boson to fermion and vice versa. You create a state that has exactly the same energy. So the degeneracy here now appears between bosonic and fermionic energy levels. And when you extend this concept to quantum field theory, to supersymmetric extensions of the standard model, as a consequence, unless you are able to break the supersymmetry, this predicts that each boson should be accompanied by a fermion of equal mass and vice versa. This is, of course, not what we observe. And this means that supersymmetry, if it's there, it must be broken, or badly broken even. Well, I mean, a large effort has now been devoted to this search. This is the CERN LHC collider, sort of aerial view. I mean, this was one of the main purposes of building this machine, was to discover these supersymmetric partners, but so far they haven't shown up. And this has led to, well, a kind of crisis at the moment. I think this is the German edition of Scientific American. I guess it also exists in Italy, Scienze or something. And I'm sure that you also have this kind of article a few years ago. This is already a few years ago. It's called The Crisis of Supersymmetry. Well, this doesn't stop us from believing in supersymmetry, because what we're looking for in these experiments is only, in some sense, the simplest versions of supersymmetry, namely those theories where you have just one fermionic charge. There's something called extended supersymmetry, which has more symmetry, and the question is how far you can go. So this is, it turns out you can go up to n equals 8 supersymmetries, and I'm just showing this without going into any details. What you get is this kind of Lagrangian. Just to appreciate Einstein's theory, the gravitational force is just here, and the rest is forced on you by the symmetry. And this is a nice depiction of the multiplet. So this is a theory that describes gravity in interaction with spin 3/2 fields, with spin 1 fields, vector bosons, spin 1/2 fields, and scalars. And in recent times, of course, once you have this highly symmetric theory, you can ask the question, maybe this theory is really able to overcome at least these mathematical difficulties, the infinities. Maybe it's so symmetric that all the infinities miraculously disappear. And this is a question that has been around for 35 years. It's not been answered conclusively so far because the theory is so horrendously complicated. However, in recent years, there's been a fantastic progress, I would actually say, really amazing progress. This is work of Zwiebern, Lance Dixon, and others that's been going on for like 20 years. And they've been able to show that at least up to 5 loops, all the infinities somehow cancel. They just miraculously disappear. This is due to, and this to me is one of the really great progresses and advances in our subject, to an insight that was inspired by string theory, namely to think of gravity, which is mediated by spin 2 tensor boson, to think of gravity as being in some sense the square of Yang-Mills theory, which is mediated by spin 1 forces. This is, of course, only a very impressionistic description of what actually happens. But in real terms, what it means, if you try to do this kind of calculation with conventional textbook technology, if you pick up a quantum field theory textbook and just follow the rules there, it's just completely impossible to do it this way, because you will have, it has been said, in order to do this calculation, you need to calculate more Feynman diagrams than there are cells in your brain. And I think already with Augusto's calculation, there was, what, 1 million diagrams? Oh, Well, you have to be very smart. And they were smart, and with clever tricks, reduced the number of diagrams. But even with this kind of improvement, you wouldn't get there. So this is a completely new technology, and they are now able to reduce this number, at least for the 4 loop. 5 loop is more complicated, to something on the order of 100 or so. Well, they don't call them Feynman diagrams anymore because they look more like this, and this is why they call them Mondrian diagrams. I like this because it just shows you how real physics, this is QED, becomes very mathematical and then finally turns into pure art. This is where we are here. Well, this result came out just like a couple of months ago. But of course, even though it shows there's extreme finiteness properties, it's not enough to show that the theory is actually consistent to all orders. And now this is a sort of debate that's going on, or is really more beliefs. Some people believe that the theory will diverge starting at 7 or 8 loops, and but maybe not. We don't know. And the fact that it's been believed for so long not to be so finite has given rise to the other famous development, which is superstring theory. And here I cannot do full justice to this because it would take a number of extra lectures to do so. But the main advantage of superstring theory over these supergravity theories is the belief that, so far still believe, that this is the only candidate theory that actually can get rid of all the infinities and all the divergences. And it does so, first of all, by replacing point-like constituents that we have in quantum field theory by extended objects, strings. And the fact that it also invokes a different mechanism for finiteness. You might think, well, string theory in terms of particle physics or quantum field theory has infinitely many excitations. So somehow you have to add up these infinitely many excitations, and then there occurs there's some miraculous cancellation. But this is not the way to do the calculation, but rather what you have to invoke is a new kind of symmetry, which is called modular invariants. And this has no analog in quantum field theory. And the modular invariance is some kind of variant of this famous duality symmetry that I mentioned. However, the proof of finiteness, so this is of course what's believed to be true, but there are no, and the other reason of course that you could get chiral fermions and possibly realistic phenomenology, but there's still severe problems. And they stand out as severe problems after 40 years. The first thing is that the proof of finiteness to all orders is, it's extremely complicated mathematics, which, even to someone like me who has done mathematical physics all his lifetime is almost impenetrable. Let me just mention this. This is just for the experts. This has to do with a property that was believed to be true up to in perturbation theory, but turns out to be no longer true once you go beyond 5 loops, which is called the splitness of supermoduli space. So that's one of the issues you have to deal with. So here at this point, it's like, many people think it's completely obvious or should be obvious, but when you try to actually do the proof, then it turns out to be almost impossibly difficult, at least for ordinary mortals like me. Next question is realistic models. And much of the superstring model building was predicated on the assumption of low energy supersymmetry. Now that low energy supersymmetry doesn't seem to be there, it's not clear what's the right way to proceed with this theory. You see, if they had discovered supersymmetry at LHC, I mean, everyone would have said, yeah, this is not just evidence for new symmetries, it's evidence for superstring theory. But the converse conclusion somehow doesn't seem to work. And one thing that has come out of study of superstring theory is that there's a monstrously huge number of vacua. So this, I showed you the building blocks of matter, the standard model. And originally the hope was, of course, that this theory would explain more or less uniquely why nature is the way it is. This was Einstein's dream, which he pursued for 26 years. He wanted to find out, as he put it, whether God had a choice in building the world or whether he had no choice. Somehow the idea being that at some point Einstein realized the beautiful mathematical principle which explains why the world is the way it is. Now what you get here is precisely the opposite. So many people nowadays think that, it's a framework. We haven't really found the proper way to formulate the theory. And another thing I would like to mention is that string theory is not the only game in town. There are competing approaches to solve this problem. There's just a list here. Not all of them aim for unification. And somehow, at the moment, there's some confusion because all of these people have their conferences. All of them believe there's somehow the right access to the quantum theory of gravity. But it's a little bit like sometimes I show a picture, a painting of the Tower of Babel. You remember the story? They were trying to build this tower, but at some point there was some horrible confusion. People started speaking different languages. They couldn't understand each other. And then the whole effort collapsed. And there's a little bit of this here too, because there's absolutely no communication, or very little, across the fence. Everyone has his own pet theory, but how do we decide which is the correct one? So let me just say, duality symmetries come back, because this is now where I put where do I invest my money? Coming back to duality symmetries, because one thing we've seen there, they play a crucial role in modern superstring theory, absolutely central role. They're probably crucial for finding this ultimate unification of string theory, which is sometimes called M theory. It already started with n equals 8 supergravity, was shown to possess this kind of duality symmetry involving one of the exceptional groups. This was Crémière-Juliat in 1979. To me, this is one of the most important discoveries in our subject. It's not always described this way, but it's really, if I were to give you a list of the 4 most important discoveries or 5 most important discoveries in our subject, this would be one. Because it provides an unexpected link with the exceptional groups, of which there are only 5. The lone wolves, they're sort of solitary members of this family of Lie groups. This is really intriguing. On one hand, you look for supersymmetry unification. All of a sudden, you fall on this other structure, which a priori has nothing to do with unifying gravity and the other forces. And it turns out that as you do dimensional reduction, these symmetries become bigger and bigger. And you can think of this as a process of converting space-time symmetries into internal symmetries. In some sense, you're trying to make space-time disappear into push the theory into some other formulation where the main thing is this duality symmetry. So, it could be that this is on the way to somehow understanding how space-time disappears at the singularity. There's this maximally extended theory, E10. After 50 years, it remains one of the great enigmas of mathematics. Let me just show you this diagram, which I already showed in yesterday's lecture. You remember this 8-dimensional diamond projected onto a 2-dimensional plane. So they had 240 vertices. This is the E10 analog of it, but there's an infinite tower of such, and they get more and more complicated. Here it's so complicated that you don't even see the points anymore on this diagram. So it just, sometimes I describe this as, you've all heard of Mandelbrot sets. Those are things that you generate, these beautiful diagrams, but you generate in a very simple way, but they evolve into an exceedingly complicated structure, and this is a kind of Lie algebra analog of this. Well, maybe I skip the next thing, but this is something we've been trying to do to sort of exploit this, although in an extremely pedestrian fashion, to somehow understand what happens with space and time as we approach the Big Bang initial hypersurface, singularity, and how it might get dissolved by replacing space-time field theory, once you get into this Planck regime, by a purely group theoretical construct that's based on this infinite-dimensional Lie algebra. This is work I've been doing with Thibaut Damour, Marc Hainaut, Axel Kleinschmidt over the last 15 years. And even after 15 years, I can say we've just been scratching the surface of this. Okay, so 3 more slides. There's one other aspect which I would like to bring up here. And this is, actually, we've written an article in Nature Physics. This is for a general audience, so this is why I give the full reference here with George Ellis. This we call the physics of infinity, because up until now, all physical theories have had a limited range of applicability, like Newtonian mechanics, it sort of, merges into general relativity or merges into quantum mechanics. But now infinity actually, so it means that, the theory is only, classical mechanics is only valid up to the point where you can neglect that there's an h bar. When you send h bar to 0, then you don't see any of this. But here, the question is now, do we always have to go all the way to infinity? Because if it's really a unified theory of everything, which is string theories, for example, claim to be, then it's a theory that must work to arbitrarily small distances and to arbitrarily large distances. So there's no limit to its validity. And the question has come up with these superstring vacua, because we're now given gigantic numbers for the number of consistent string vacua, and each of them in some sense would describe a different universe. So this has now fueled a debate about whether the universe that we see is just an infinitesimal part of something much, much, much bigger, a megaverse or multiverse, and maybe it's such that all these theories are realized in different universes. We just happen to be in the one that allows us to exist. Now, David Hilbert was one of the great mathematicians of all time. In 1925, wrote an essay. It's called on Infinity, or the Nature of Infinity. And in this, he states very clearly, the infinite is nowhere found in reality, no matter what experiences, observations, and knowledge are appealed to. By this, of course, he means real infinity, not simply infinity as a substitute for a very large number. Infinity is much, much larger. It's also much, much larger than this. You don't even get close to infinity, even with this number. So the question is really, finally in nature, is infinity, when we use it in physics, is it just a placeholder for a very large number, as would be the case if the number of string vacua was very large, but still finite? Or is it what you might call essential infinity, which brings in kind of paradoxical things like, have you heard of Hilbert's Hotel? It's an infinite hotel. This is a hotel, even if it's fully occupied, you can always get a room there, because the rule is then you go to this hotel, it's fully occupied, but then the person at the reception says, you know, everyone moves to the next room. You just keep going, keep going, keep going. So this is what's called Hilbert's Hotel. And you can sort of think up all kinds of paradoxes with this. And just to come back to my favorite idea, it could also be that, you know, exponential, this is something that we see in E10. It's an exponential increase in complexity that you don't see in finite dimensional symmetry groups. And this could actually be such that as we try to approach the Big Bang with our understanding, it could really, you know, we could hit into a kind of non-computability in a mathematically well-defined sense that would prevent us from ever getting to this point t equals 0. Okay, so I'm almost finished. Once again, where do we stand? And I should say it's now, especially in the light of the LHC results, the failure to discover dark matter. So far, at least, there's been no signs of deviations from Einstein's theory or Einstein's equations from gravitational wave measurements. It all seems to fit perfectly. So I thought I found a nice summary of this. This is also a theoretical physicist. He gave a talk in Cambridge, Unsolved Mysteries of Fundamental Physics, to chemists. Okay, so here's the abstract. He says, in this century, progress in fundamental physics has been slow, true. The Large Hadron Collider has not yet found any surprises. Attempts to directly detect dark matter have been unsuccessful. And here he put actually string theory. So he says string theory string theory has not made any successful predictions. Now here I would put none of the available ansatz, because for some others it's even worse than for string theory. So none of these available ansatz has made any successful predictions, and, well, nobody really knows what to do about any of this. So some of my colleagues are a bit depressed about this state of affairs, but I would say it's just the other way around. Now we have a great challenge. You know, we see something, we want to explain it, and the theories that have been put forward to explain what we see so far have not worked out. So I think these are great times for aspiring young theorists. You know, what we need is really a great new idea, far beyond what's been known so far. So to conclude, I would like to conclude with two beautiful quotes in your mother tongue. Here they are. One is from Galileo Galilei. Have you seen this? You know this? The first one. It's kind of famous. Well, I don't have to translate it for you, of course. Although, you know, I showed it to I have two Italian PhD students. I showed it to one of them because we were debating, you know, I was a little bit confused about Italian grammar, about the plural endings, but this is correct, he assured me. But he said to me, you know, when I read these Galileo sentences, you know, I have to read them 5 times to understand what he really means. But what he really means, I think, is that, I mean, he really already sees some connection between the very small and the very large. This is, and of course, you know, saying that it's a vain enterprise is not so discouraging. So that part I would ask young people to ignore. Second one is Albert Einstein. This is actually from the original German, which I was able to translate with some help from my Italian PhD students. And here he says, so Einstein said that if God really created the world, his main worry was surely not to make it such that we could understand it. And well, maybe that's the case. So thank you very much for your attention.
And then you see what I mean, right? You start with Newton.
This is the one.
No. Very beginning.
This?
No.
No?
Very beginning. Very beginning.
This is the very beginning.
Oh, is it?
I mean, this is...
Sorry.
Yes.
It's okay. So it's okay. Now, is it fair to say that, all what to say is very daring and very interesting. However, I wonder whether you accept the following observation, that in fact, you see, the redirection in those steps at any time, right? Perhaps with one exception, which I don't really see, which is Einstein, really. Came from actually, new observations,
exactly,
new observations.
Exactly, yes.
So
True.
that is a fair statement,
yes.
no?
Yeah. Exactly.
So
up to certainly up to here, it's based on observation. Yes.
Right.
Including quantum mechanics.
So you are not discouraged by this.
No, I still maintain. I think. I would still think that ultimately there has to be some observational verification of what we do. You see, the confusion at this time in our field has to do with the fact that no one is able to make a prediction with which the theory stands or falls. With guts, you still have that. You say that the proton will have to decay with such and such lifetime. So that's, in some sense, you can already use that to make a prediction that can be tested against.
No, but you see, I'm not really referring to, say, falsifying theories or proof that some theories are right. I am referring to the fact that historically, experimental observations have been crucial in redirecting this attempt to find a unified description of nature.
Right.
No, that is, I think, correct. No.
This is correct. In fact, I think it's even correct of Heisenberg, because Heisenberg, at that time, they had proton-neutron. As you may know, he didn't like the eightfold way. Gell-Mann, he thought there was not a really, truly fundamental way to think of particle physics. He had this idea that isospin was a fundamental symmetry and therefore had a spinner. And then he tried to write down an equation that would just work with the spinner. And on top, it had a fundamental length in it. And he thought the length was 1 Fermi. So he was simply concerned with understanding or trying to understand particle physics. Why he left out gravity, I don't know. I mean, this is a big hole in this attempt. Just like with Einstein, Einstein left out particle physics. He just tried to unify gravity and electromagnetism. He simply didn't take note of what people were doing at the time in particle physics. In fact, I remember once talking to Steinberger and said, you were with Einstein in 1949 at the Institute for Advanced Study. And then he said, he never talked to Einstein because he was very withdrawn with these attempts. And he took absolutely no interest in what was happening in quantum field theory and particle physics. He was just not interested. It was so